Question number 7 of JEE Main 2016. A pendulum clock loses 12 seconds a day if the temperature is 40 degrees Celsius and gains 4 seconds a day if the temperature is 20 degrees Celsius. The temperature at which the clock will show correct time and the coefficient of linear expansion alpha of the metal of the pendulum shaft are respectively, and then the options. Let's see what is coefficient of thermal linear expansion. It's the fractional change in size per degree change in temperature. So what we consider is the fractional change. Fractional change is delta L upon L naught, which is equal to alpha times delta T, where alpha is the coefficient of thermal linear expansion. Now this fractional change is important because the reason we consider the fractional change is that no matter at what temperature the metal is at, each degree Celsius change will have the same effect on the fractional change. So let's say if it is at 20 degrees Celsius and the temperature changes to 21, or it's at 25 and then changes to 26, this fractional change will remain the same. It will not change. The fractional change is constant. Or let's say if the change in temperature is not 1 degree Celsius but it's 2 degrees Celsius. In that case, the fractional change will also double, because if there is a change in 2 degrees Celsius, that means that it will change twice of what it will change for 1 degree Celsius. So that's why we consider fractional change, and that's why it's relevant. Now let's see what is given in the question. It's given that the clock loses 12 seconds a day and at 40 degrees Celsius and gains 4 seconds a day, which means that at 40 degrees Celsius the clock is actually moving slower, and at 20 degrees Celsius it's actually moving faster. So the ideal temperature at which it neither loses or gains any temperature has to be between 20 and 40 degrees Celsius. So that's kind of intuitive. So it should be between 20 and 40 degrees Celsius. So the range of temperature is 40 minus 20, which is 20 degrees Celsius. So in this question we are concerned with a range of 20 degrees Celsius. And what happens in this range? If I draw a number line right here, in which let's say I represent 4 second gains in this way and then 12 seconds loss in this way. So this total range is around 16 seconds. It's exactly 16 seconds. 12 seconds on this side. So I can say that 20 degrees Celsius, a change in 20 degrees Celsius, 40 minus 20, corresponds to 16 seconds in this clock. So 1 degree Celsius would correspond to 16 upon 20, which is 0.8 seconds. So for each degree Celsius, there is a change of 0.8 seconds in the clock. Now, if 1 degree Celsius corresponds to 0.8 seconds, I can say that 12 seconds, since it's given that there's a loss of 12 seconds would correspond to 1 upon 0.8 multiplied by 12, which is 15 degrees Celsius. Now, if 12 seconds is 15 degrees Celsius, it means that at the ideal temperature at which there is no loss of 12 seconds is 40 degrees Celsius minus 15 degrees Celsius, which is 25 degrees Celsius. Now I can also find out what would it be for 4 seconds, since there's also a gain of 4 seconds. I can say that for 4 seconds it is 1 upon 0.8 into 4, which is 5 degrees Celsius. So the lower temperature, the 20 degrees Celsius, at 20 I can add 5 to it, and I will still get 25 degrees Celsius, which kind of double confirms that we are at the right temperature. So what's really happening is that at 40 degrees Celsius it's becoming hotter, so the length of the pendulum shaft is increasing, and we know that T is equal to 2 pi square root of L by G. This is the formula for simple harmonic motion, where T is the time period it takes for the pendulum to make one swing. So in this pendulum, if it is swinging from here to this place and then coming back, that corresponds to 1 second. So this time period is equal to 2 pi times square root of L by G. We can see that L is directly proportional to T, So at hotter temperature, 40 degrees Celsius, this length will increase, and so time period will increase. And at 20 degrees Celsius, this length will be shorter, and that's why the time period will go down and the clock will gain 4 seconds. It will become faster because this motion is happening faster when the length is decreasing due to cold temperature. Now what really happens at in a day? Let's say that in a day it loses 12 seconds. Now how many seconds are there in a day? In an hour there are 3600 seconds, multiplied by 24 will give you 86,400 seconds. So there are 86,400 seconds, and the clock loses 12 seconds, which means that the clock is actually taking 86,412 seconds to do 86,400 swings. So I hope this is quite intuitive. Since it is losing 12 seconds in a day, then it means that it will take 86,412 seconds to do 86,400 swings. So which comes to around 1.00014 seconds. This is an approximate value. So it's actually taking longer than a second, and since it is taking longer than a second, it's gonna get slower, right? So for each second, for each swing, it's taking these many seconds. Now if this is the time period and we substitute this value in this formula T, we can find out the length of the pendulum shaft when, right? So when this increases 1.0014, it can, at 40 degrees Celsius, it will actually give us the length. So let's substitute 1.0014 is equal to 2 pi square root of L by G, which will give us L is equal to 1.0014 upon 2 pi times square root of G whole square, which comes to 0.24811. So I have just cross multiplied and moved things around so that you can see. So that is the length at 40 degrees Celsius. And then what is the length at normal temperature, or at 25 degrees Celsius? At 25 degrees Celsius, this time period will be 1 second. It won't change. So I can substitute T is equal to 1 in this formula, and I will get 1 is equal to 2 pi square root of L by G, which will give me L is equal to 1 upon 2 pi square root of G whole square. Just moving things around, and then that comes to around, I will substitute for G, I will substitute 9.8 meter per second square. So that comes to around 0.24804. So we can see that this length is different from this length. So let's subtract these two to get delta L. So I will subtract 0.24804 from 0.24811, and that will give me right here, that will give me 0.00007. that is delta L. Now I can use this value and this value in this formula right here, delta L upon L naught, to get, and I know that change in temperature is 15 degrees Celsius. 40 minus 25, 25 is the normal temperature, 40 is the increase in temperature. So 40 minus 25 is delta T. So if I move things around, and then I'll get alpha is equal to right here 0.00007 upon 0.24804, which comes to around 1.88 into 10 to the power minus 5. Now this is not an exact value. It's in the question it's given 1.85 and I got 1.88, but it's close enough because I have been rounding off values. But even if I round off values, the 10 to the power minus 5 part will not change, and there's only one option in which it's 10 to the power minus 5. So the correct option is the first option. This is the correct option. And in this question I could have stopped at 25 degrees Celsius when I got 25 degrees Celsius, and that's it. But it's good to know where how to calculate alpha. And If you'll check in the description, I've tried to show how this question could have been solved in a much shorter time. And if you're interested, please look into that video. And if you liked my solution or like my video, please click on the like button and subscribe, and share and comment. Please comment how did you like this video.